I need it for something.
The green. Yeah. I'm not going first. Caleb is, Oh, Nathan. It's just like.
Hello, good morning. My name is Caleb Mertz. My teammates are Alexander Smalley, Kayla Godelucian, Megan Austin, and Sydney Fang. We're here representing No Baby Go, Team Baby Gotti, and our advisor is Professor Eva Johnson. As an outline of what we're going to talk about today, we're going to look at the project overview real quickly, the user interface, what the user interacts with, the Bluetooth remote control device that we've implemented for the vehicle, the full electrical system, the different components of that, and then the mechanical system, a lot of items we've added and modified, and then lastly what we've learned. So as a project overview, we've developed a kit to be assembled by non-technical adults onto the Power Wheels vehicle, specifically the Wild Thing model. This is for children with different movement disabilities, such as cerebral palsy or spina bifida. We have different control options depending on the child's needs that can be implemented. And we also have a remote control device for a parent or physical therapist to be able to steer the vehicle remotely. So I'll first talk about the user interface. So as an overview, the user, so the parent or physical therapist, can select among different types of control options to be implemented onto the vehicle depending on the child's needs. These control options plug directly into black box or electrical blocks. And the parent or physical therapist has the option to stop the motion at any time with a kill switch. So, just going real quick through the different control options that we have a single button presented here by Megan on the screen. This can be used as a single button or as double buttons on either side. Then we have the single joystick. This is the Adafruit small arcade joystick. Then the foot pedals being demonstrated by Kayla here on the vehicle. And then existing joysticks, so the way it came out of the box. And then also a Bluetooth remote control device, which in our case is actually an app. So going back a ways, we originally started with the Raspberry Pi as our main control system, kind of the brains of the system. Eventually we switched over to the Arduino Do because of multiple different reasons at the time, some of which you'll hear about a little bit later with the amount of analog outputs. We originally also had modes to switch between the different control options. There were some struggles there with different types of modes conflicting though, and also we came to the conclusion that a child would probably stick with the same types of control options for quite a while. So there isn't really a need for being able to switch between different control options from the circuitry on an electrical standpoint. So you can upload simply a different program based on what type of control options are being used. Next I'll talk about the Bluetooth remote control device. So since we switched over to the Arduino, we also had to switch over to a Bluetooth module. We went with the HT05 since the Arduino does not have onboard Bluetooth as the Pi did. So this is a pretty standard module and fairly easy to interact with. And along with that, because we decided to switch the modules, we also went from an external control device, as this controller on the left side here, and switched to an actual mobile application. So this is a mobile app that exists on the App Store for free already. It's called the Arduino Bluetooth Controller. And it's basically set up there to be used for different types of projects. And this works fairly well for what we're doing here. So when you first open the app, you can connect to any Bluetooth device. On the screen here, we have the HT05. You can see there that we'll connect to. Once connected, there's different options. For our usage, we only use the vehicle mode, which is the top one. The bottom three will not be used in our implementation. So once clicking on that, you get to this screen. So on the left here, you have three different buttons. Right now, we're in stop mode, which is that top button. And then the middle mode, and then there's a bottom mode, and I'll go through those. So the stop in this mode is you can move the phone in any direction, and the vehicle does not move at all. So nothing happens in this mode, pretty much it's kind of a standstill. Now if we switch to the middle mode, it's auto mode, this is where the child actually has full control of the vehicle. So there they can use whatever controls they've implemented on the vehicle to drive themselves. And at any point the parent can click on stop to go back to that mode to stop the vehicle also. And the last mode on the bottom here is the manual mode. And this mode is for the parent or physical therapist to actually drive the vehicle themselves around the room. So this would be used, for example, if a child is moving towards a wall, they can stop it and then turn them around and move them in a different direction, for example. So how this works is it's actually based off the tilt of the phone, which is nice because the parent can look at the child while moving the vehicle so they don't have to try and click any buttons on the actual screen. So if I tilt the phone forward, for example, you can see that right slider. It tilted forward, that right slider moved up to show like, where the orientation of the phone is. I'm going to go back to this mode real quick, stop mode, and if I click on the top right, there's a set commands option, and this is why we like this app. Because if I click set commands, all of the values that we use internally in our code can be inserted into the app directly. And this is something that's clearly explained in our documentation for the user to do, but this means that there are a lot of different types of apps out there that actually work with our system. So also on an iPhone or maybe even another type of device. Because basically the app knows to send these specific values on a specific movement. Next I'll pass it over to Sydney and Xandra for the electrical system.
Thank you very much, Caleb. All right, so as most of you remember, these 5 wires coming from the joysticks were the bane of our existence for most of this year. We spent a good portion of this semester and all of last semester just trying to understand how these 5 wires came, how they worked, what the differences were between the joysticks, what the differences were between the cars, and then how could we then emulate these signals. So as you may remember or may not, we have 5 wires, red, black, white, yellow, and green. We determined that the red, white, and yellow wires were stationary in value. They don't change. They're either set at 0 or 3.3, depending on what wire they are. So it was really just the black and green wires that we had to worry about. So you might remember seeing this plot before, but you can see that the green wire is actually a ramp function here that goes with the movement forward of the vehicle, and the black wire is a step function shown in the blue outline. So then once we had determined these signals, we had to then figure out how to emulate them and then how to implement them. So how that came about was through our electrical control system. So this is for the kit. So up here you can see control 1 and control 2. Those are the inputs to our black electrical box. That can be either one joystick, that can be 2 buttons, that can be 1 button, whatever configuration the child needs. Both of these ports do not need to be filled in order for the Arduino to go as it is supposed to. Over here you can see we have a portable cell phone charger that is powering our Arduino, and then in the middle of that is a kill switch. It's just a nice little toggle switch that is on the outside of our vehicle that a parent or physical therapist can easily access in order to stop the movement of the vehicle. So then coming from the Arduino, those are all going into, this is coming out of. We have the red, white, and yellow wires. Those are all being emulated as their stationary values, so we did not have to mess with them too much. They just passed from the Arduino to our main circuit board. However, the black and green wires, because they have ramp functions and step functions, we needed to pass them through digital to analog converters. Now the Arduino has 2 internal digital to analog converters, which is what the black wires pass through, and then those signals go to op amps, which boost the signal to its full 0 to 3.3 volt range. The green wires go through external digital to analog converters, and that does not need an op amp circuit, and then everything passes into our main circuit board, correctly emulating the signals as the joysticks on the out-of-the-box car would have. So this is a slide of hardware we used. Up here you can see our Arduino do. Here is our kill switch. It's just a nice, pretty big, size of your thumb kill switch that has a very satisfying toggle factor to it. Down here you can see our external digital to analog converters that we use. And up here is the lovely perf board that Alexander spent a good amount of time working on. And that has our op amp circuit here on the top, as well as these digital to analog converters. Now, all of this is housed in our black or pink and green box. This is where all of our groups, all of our electrical stuff is housed. You can see here, we have the perf board, our Arduino is below that. This black sliver right there is our portable cell phone charger. So that fits very snugly in there, and it all buttons up quite nicely and attaches to the back of the vehicle. And right here, it's hard to see in this picture, but there is the external kill switch, very easily accessible by a parent or physical therapist on the back of the car. You just have to run up and toggle the switch one way or another. So with that, I'm going to pass it over to Xander to talk about our favorite 7-year-old.
So Aldine is the child that we've been fortunate enough to work with over this past year. We're making specific modifications on a car to best suit his needs. So we've been able to talk with his parents and physical therapists to be able to determine the controls that would be best suited to him. So as you can see here, this electrical setup that we have for his car specifically has a lot less going on than the one Sydney went over just a little bit ago for the kit car. So as you can see on the right here, most of the wires actually just get passed pretty much straight through. We found that we didn't actually have to hijack the yellow, white, black, or green wires, and we just tap into the red wire, which supplies power to the car. And that goes through both of the foot pedals that we have attached on his car and through a kill switch that we have as a safety feature before going back to the main circuit board. So this is a setup that we determined best suited his needs. He has to push both of these foot pedals down in order to then use the joysticks that come on the car already as they normally would. And this was determined to be good physical therapy for him to strengthen his legs so that he has to keep those pushed down in order to use the car. So then some of the differences between Aldine's car and the kit car. One of the biggest ones is that we discovered that Bluetooth cannot be integrated with the existing joysticks. So in the kit option you see Bluetooth can be integrated with all of his other options, but not with the joysticks that are on the car. And this is due to the analog nature of some of the signals. For the kit, the Bluetooth just sort of hijacks that emulated signal that we're sending out. But we couldn't switch between the actual signal and the emulated, well, because of the analog. So then with Aldine's car, the other big difference than just like a generic kit car rather, is that the foot pedals that I mentioned earlier, they have to be pressed down, and then that allows the actuation of the motors by the joysticks like normal. And then in the kit car, obviously unlike Aldine's, there's multiple different options available rather than just having one specific setup that's customized to his needs. So now I will pass it over to Megan to talk about the mechanical systems.
Thank you, Xandra. So I will talk about the details of the mechanical systems we've incorporated into our vehicle. So what I'm showing you here is this is the out-of-the-box car. So if you buy this car from a retailer, this is what it looks like out of the box. So I'll use it as a reference to show what we've built to accomplish. So for Aldine, as was mentioned in previous presentations, we had to add a specific seat for him. So this picture on the top left is showing the seat that we added, and it was our first configuration. And you can see that back angle is very reclined. And his physical therapist requested that we further increase the angle, and that is the picture on the top right. So you can see that the angle is very much so forward. And we achieved this by inserting a wedge right here in between the original seat and the new seat on the vehicle. And this was simply made out of a wooden block that we covered with felt. So it did the job in between the two seats. We also added 2 leg cushions to the seat. His physical therapist was concerned that while he was actuating the foot pedals, his knees were opening and causing potential further injury to him. So we added these leg cushions just to keep his knees and legs aligned. So another change that we made to the vehicle, on the left, this is the back wheel that comes on the car. And you can see that Fisher tried to add a couple of indentations on there to increase the friction between the wheel and the floor. But we found that on most floors that this car will be driven on, that this was not enough. So we added a simple bike tire to that wheel just to increase the friction between the wheel and the floor. So as mentioned, two options are the single joystick and the single button. And in order to use these controls, they would have to be situated in front of the child for easy access. And this is done by this control mount that we've come up with. So with this control mount, this height can be changed in order to best suit the child's height and size. And it can also be moved medially or laterally to the body. So if, for example, a child needs to work on his or her right arm, they can move it towards the right side of the body versus the left. And none of the children in our section or section A needed these controls, so it is not, the mount is not fixed to the car. We're just simply holding it in this photo to show you how it would attach to the vehicle. And now I'll pass it off to Kayla to talk about the foot pedal houses.
Thank you, Megan. So these are two of our foot pedal housing options. The reason we have to have a housing is, as you can see in this top right photo, the foot pedals that we bought come with a plug, and it makes it a little difficult to attach to the car. So the first housing we made on the left, we took that to Aldine in February, and it worked for him. However, it was a little bit too close to the seat and didn't give him a lot of leg room, and so especially as he grew, it was a concern that he wouldn't be able to use the car for a long time. So we switched over to this other design. This also works with the optical sensor mount that the Section A group made, and it's just built on top of that. And in this photo, you can see how it is attached. It's made out of Ninja Flex, which is a more flexible 3D printing material. And that way it slides onto the bar really easily, but it's also very strong and it won't break. Now I'll talk about the mechanical testing that we did. So for the control mount, we needed to do a test to make sure that it didn't break if the child was just using it regularly, but that it would break if the child hit a wall and went flying forward, because it would be more dangerous to the child if there was something sticking out towards their stomach than if they just fell all the way forward. So for the first test, this was just for the 10 pounds if the child just applied the force to use the joystick or button. As you can see, there wasn't really a lot of stress applied to the mount. However, for the 100-pound test, it was made where it would break at the bottom, and so this proves that it would, if the child fell forward, then they would get injured from this. And then we also wanted to do a further analysis because 100 pounds is at the high end of like the child's weight limit. So we discovered that it would fail at 30 pounds if the child fell forward. The other testing that we did was for the foot pedals, and we did again another 10-pound weight for if they press down on it. And we used the crane scale for this by attaching it to the foot pedal and pulling it back and then waiting until it showed 10 pounds. And this really didn't affect the foot pedals at all. They barely moved and it did break, so this was considered a pass. And now I'll pass it back to Megan to talk about what we learned.
Okay, so a couple lessons that we've taken away from this past year. First, reverse engineering was one of the biggest problems that we ran into. So using a vehicle that was already designed by Fisher-Price, we had to understand how the connections worked before we could actually build on top of that. So our electrical team worked probably more than half of this project length simply doing reverse engineering. Second, connectors were also a big problem for our MCC team. The connectors that came with the vehicle were almost custom. It was something that was very difficult to find and therefore implement with our new black box. So they ran into some troubles with that. So I don't think any of us had experience working with disabled individuals before this project. And one of the big lessons that we learned is speaking positive language while working with these folks is very important. At no point did we want to suggest that the children were limited or disadvantaged because of their disabilities. We wanted to keep that language very positive while we were helping them with these problems. We also learned a lot about iterations. We probably had to redesign things 3, 4, 5 times before they actually worked. And it was okay to fail a couple of times before we found the solution that worked the best. And finally, you can never start too early. So as a summary, we talked about our project overview and the goals that we had this past year, the user interface, the Bluetooth remote control device or app, the details of the electrical system and mechanical systems, and we wrapped up what we have learned over the past year. And finally, we show a little video of Aldi driving the vehicle in February. We first took it to him at the mobility lab. So he really enjoyed it. He really liked the color, he liked how it worked. That's his father recording behind him and his physical therapist as well. So they were there to help us give any advice or any concerns that they had with the vehicle. So thank you. And I have any questions.
So the phone app, you were talking about how it kind of works on tilt.
and so forth. So if you tilt it forward, the device goes faster forward. Is that how you?
Yeah, so the question was if with the phone app, if it goes faster as you tilt it, or with the movements on the phone app. And how that works is actually there's just a ramp-up function in the code itself. So it actually does not tilt the amount that you tilt it. It is simply a digital, I guess, signal where if it is forward, it will ramp up, and immediately if you move it back, it does cut that out to stop again. Or if you hold it, it will continue to move.
Kind of like an emergency stop? You're not driving it remotely?
So no, you can drive it remotely, I'm sorry.
Okay.
But I'm just saying, like, if you are moving forward, if you hold it forward, it'll like continuously output a specific value, and that value will continue to drive forward, or left, or right, all options work. But if you hold it center, move it back to the center, then it will stop.
And the crux to my question is, what if they drop the phone?
If they drop the phone, it will land upright, because hopefully it won't land on the edge, and it will stop again. If it lands on the edge, then that's bad.
Okay, so face down or face up, then it stops.
Yes, correct.
Right.
This is a question perhaps about teams, but I'm imagining it. Did you try to kill the switch, use the kill switch while it was spinning full speed, trying to chase it? So I'm trying to imagine reaching the kill switch while it's in full motion, rotating, and it's always going away from you.
The question was how the parent physical therapist could easily reach the kill switch if the vehicle is moving pretty quickly, even spinning away from the adult. That is something we tested a little bit. It is, of course, not always an easy task. We did place the kill switch in a very good location, though, to where it was probably most easily accessible for the parent physical therapist. But also that's one reason that we do say it would be best to use the app also as an additional feature, because you can go in that automatic mode and just leave it there, but if you see something going on, you just hit stop quickly. So there's a give or take for each option.
Along with that, the cars are moving about 2 miles an hour, so it's not going, the car's not driving away at like 20 miles an hour. You don't have to be fast to catch up with the child. Along with that, most of the cars that they already have at the Ability Lab have something very similar where it's a switch either on the front of the vehicle or on the back of the vehicle. So we tried to emulate what they did at the Ability Lab with this, and it worked out pretty well.
One following question. If the phone dies while it's moving forward, will it stop? If the phone battery dies, will stop sending the signal?
Yeah, that's a good question. So the question was, if the battery dies or loses connection or something, does the vehicle stop? And after testing, this was actually one of the tests that failed on our side, is that if it does stop for a moment, but then the child can continue to use their controls. So it does stop it for a moment in case they were going fast into something, but then they could continue forward to the side. So that's something that we, moving forward, want to test out and work on. Any other questions? Thank you.
It can slide it.
Here you go.
Huh?
So I have a tablet that slide on my watch.
Yeah, I said sure, I don't care. Alright, so what I'm thinking is we're not doing the island. We're abandoning the island strategy. That was a dumb strat. We're gonna go 3 and 2. So it's gonna be.
We're not doing that?
No, we're gonna go you 3. Because you go first, third, and fifth, and then me and Haas on one side. So we're not moving back and forth to and from the island. Yeah, I mean, the mag pass off's gonna be the same. She's gonna pass it up to you when she goes back. Haas gonna pass it up to you, so it doesn't matter. Yeah, so you 3 are gonna be standing by each other. Me and Haas are gonna be standing by each other. Yeah, Haas going second, I'm going third. Daisy's going first, you're going third, and Luke's going fifth. So yeah, so when she's done.
Do you know where your section is? Hey, remember,
It's right here.
Alright, we're gonna get started.
Alright, hello everybody. My name is Danielle Desmond. I am here with my team, Andrew Teaming, E.D. Jagal, and Katie Harrell, talking about our system, the gatekeeper system. Our advisor is so today we'll be telling you a little bit about our project definition, the system overview, our subsystems, the results, our lessons learned, and then we'll have some time for questions at the end. So the project definition was, as you all probably know, to create a wearable biometric gait identification system that will properly identify our user within 20 seconds or 10 meters based on their walking gait. And now I'm going to tell you how we did that. So this is a quick system overview of our 2 major systems, which is our data collection system and our data processing system. So we have kind of our hardware electrical systems and then more of our software systems that go through the identification process. So these are some of the hardware components that we will tell you about today. So our first one that we're going to look at is the accelerometer gyroscope, our GY521 model, which is a 2-in-1, which is great for us. We'll also tell you about the multiplexer, which was necessary to interface with the accelerometer gyroscope because it uses I2C protocols. We'll tell you a bit about our Arduino Micro, which is kind of like the brains of the operation. We'll tell you about the housing for some of our hardware components, including the Series 8 running belt. We'll tell you about our new compression sleeve, which we need in order to actually use our system properly, and we'll talk about our Bluetooth module, the HC05 Bluetooth Classic module. So here's a quick overview of our wiring diagram, which has our Arduino Micro right here, our 3 accelerometer gyroscopes right here, our multiplexer here, and our Bluetooth here. So we're going to tell you, oh, I forgot that I had that there. But so here's everything kind of highlighted for you. And we are going to continue and talk about our GY521 accelerometer gyroscopes. So this is kind of our main part of our electrical system. It's one of the most important parts because it's how we get our data. So what type of data can it give us? Well, it can give you a raw acceleration data, raw angular data, Euler angles, or yaw pitch and roll. And so all of these parameters can be sampled and pulled at any point in time that you so choose. It can also sample up to 8 kilohertz of a sampling rate, which is pretty fast. And the Nyquist rate is approximately 15 hertz, which is, again, really kind of fast. And the data that we utilized with our system was actually the raw angular velocity, which we can talk about a little bit later as to why we chose that. And then I will hand it over to Eugene, who is going to talk to us about our multiplexer.
All right, so this is the TCA 954-8A 8-to-1 multiplexer. And it is specially designed to work with the I2C serial communication protocol. That protocol is bidirectional, which is why we can't use a simple multiplexer because those are normally unidirectional. So the reason why we needed this multiplexer was because the sensors that we actually have only have 2 available addresses using the I2C protocol. However, we have 3 sensors. So in order to get around this issue of not having enough addresses to allocate, we were able to use a multiplexer to expand the amount that we had. Now, you might be wondering, well, if you have 3 sensors, why do you have an 8-to-1 multiplexer, not a 4-to-1? Well, the original design actually called for 5 sensors, which would require 3 bits to quantize. However, afterwards we realized we only needed 3, but we still had purchased the 8-to-1 multiplexer, so if you had a 4-to-1 multiplexer, that would also be sufficient. However, we did not want to increase costs in order to meet a redundancy. So anyways, after you collect the data using the I2C protocol with sensors, you have to transmit them. And you can transmit them through the air through usage of Bluetooth using the HC05 Bluetooth module. The original design had called for the HM10 Bluetooth Low Energy module. However, we realized that Bluetooth Low Energy continually pushed us out of the scope of the project because the development for that is mostly geared towards mobile applications, for example. So all the research that we're trying to find kept pushing us towards creating a mobile application, which is not part of the project. Also, other characteristics of the Bluetooth Low Energy classification is that it just doesn't meet our design criteria. So we have throughput issues as well as connectivity issues. Our data should be sent in a real-time manner, so what comes in immediately goes out, whereas Bluetooth Low Energy isn't really sufficient for that. However, a full channel using Bluetooth Classic 2.0 is quite sufficient for that application. So as a result, we're using the HC05 Bluetooth module. And we use this module to transmit the angular velocity on the X, Y, and Z axis. So on the other end, we actually have a local machine with MATLAB installed. And through that, we're able to use the IDE's libraries in order to communicate with our device that has the Bluetooth module on it. So we have a script to search for the device, and that's actually completely separate, and it only needs to be run once. The reason why is because it takes a very long time to create the Bluetooth object once it's found, and that's just a matter of the algorithm being agreed on the library. So we made that separate, and it only needs to be run once prior to any other collection of data. Afterwards, you can run a data collection script, which will actually have the local machine with MATLAB on it act as a client and send requests to the server, which is going to be the Arduino Micro, which I'll discuss in a moment here. And that will send a data request in order to collect data, and then you can also request to stop sending data in order to preserve power and to notify the device that you don't need any more data. So next is the Arduino Micro, and the Arduino Micro is effectively the server, per se, and it's what is controlling the wearables part of the system. So it acts as, like, let's say, the brain, for example. So it's going to be what is trying to wait for that polling from the client. And it's also going to be what is going to gather that data and eventually send it. So we have a couple of tests here. So the first one we have is power supply usage, and we decided that our power supply should not exceed 10 volts, as well as it should be able to run for at least 2 hours continuously, assuming full capacity of the battery to begin with. And in the top here, you can see that our readings are all below 10 volts. These readings were taken before the device was left to idle for at least 2 hours, in that test, we checked routinely every 15 minutes to check if the system is still running and is still powered. The ones indicate that the trial succeeded and that the power was able to be delivered. You'd see zeros if it did fail, but it managed to pass throughout all the trials, as well as testing the sampling frequency. So we had a minimum sampling frequency of about 20 Hz. And we had a program that would actually output sampling period using data pulled from 3 accelerometer gyroscopes, and using that, those numbers, we could take the inverse of that in order to find our sampling frequency, which ended up being an average of about 50 hertz, which is over about 2.5 times the requirement. Some improvements we could have is that when we were testing, a lot of times we ran into issues regarding wires disconnecting and detaching. When that happens, the system tends to halt and completely fail. And we were able to accommodate for some of these issues by detecting where or which wires tend to detach the most. And we were able to either reinforce those connections through a little bit of soldering or simply just taping them down. We did use a breadboard. However, I think using a perf board and soldering all the wires together would actually eliminate a lot more troubles with detachment. Another thing that we could implement is sleep mode. So that is actually telling the processor on a machine, for example, to sleep, idle. And correct usage of sleep mode in an embedded system will drastically optimize the power consumption. That's how many people are able to, for example, get devices to run for years on a single battery. And another thing that we had issues with too was when we originally had issues with detachment and the system failing and halting, we might have had a couple of data samples, and perhaps we could actually use that still to identify a person. But with the current design, we never actually handled that. So perhaps for future purposes, we could attempt to identify a person if, in the case, the device halts, but we still have some data collected. And now I'm going to hand off to Katie, who's going to talk about mechanical systems.
So I'm going to start with the evolution. The biggest part of what has changed throughout our process is reducing the number of components that we use. Originally, we had it set up like the figure on the left using 5 sensors spread across 2 legs. Now we've cut it down to 3 sensors on one leg, a sensor on the right shank, right thigh, and one near the belly button. Another big change that we've had is to our accelerometer housing. Our original design is on the left, and then our new design is on the right. It's gone through multiple iterations, but this is the most recent and our final. A lot of the big changes that have been made is that it has been made larger because we realized with our wiring and everything, we'd take up a lot more space than we expected having just the accelerometer. We have also added, we changed the lid so that it's easier to access the accelerometer because our original design is very hard to get in and out. We've added those 2 cylindrical extrusions on the base of it that fit through the clearance holes on the accelerometer to help hold it in place. There's also a notch on the left that was put in because we realized once we soldered the headers onto our chip, they would protrude downwards and then it would cause our accelerometer to not run flat, which would cause a problem with a lot of variation in our data. I'm going to go through the mechanical subsystem testing. The first test that we did was on sizing. According to our SDRD, the portion on the leg had to fit between 15 and 22 inches, and on the waist between 25 and 45. We got these numbers based on where our parts to our system would be on the body, and also the change in size for our running belt. All of us took 3 measurements, got the average, and since they're all green, we all fit within the ranges that we needed. Another test we did was for range of motion. We made it clear at the start that our system could not change the range of motion that we would have naturally. We decided to use the functional movement screen standards in the deep squat and an inline lunge. That way we would keep it pretty standard across all of us. We did 10 iterations of each, and we calculated or measured knee flexion and hip flexion. And then we did 3 iterations of it while wearing our knee compression sleeve to make sure that nothing changed. Our averages while wearing the compression sleeve were within the average plus or minus the standard deviation without it, so we considered that still having a normal range. Our next test was about piercing, bruising, and lacerating the user. That would obviously not be acceptable with the wearable system. We took photos before putting on our system, after wearing it for 20 minutes, and 20 minutes after removing it. As you can see, there are no pierces, bruises, or lacerations that were not there originally. We do have, it's hard to see on the screen, but across the thigh, there's some indentations because the knee compression sleeve is tight, but those faded pretty quickly. We also had in our SDRD that no direction on our housing on the lake could be larger than 3 inches. We measured them all in the X, Y, and Z direction, and the largest side was 1.2 inches, so we were much smaller than we expected initially. We also decided that our system could not be more than 5 pounds, and our average weight was 0.74. Some improvements that we could make on our system are replacing the unique pressure sleeve with pants. It would make our system a lot more comfortable and presentable. We could also replace the accelerometer housings in pockets if we turned it into pants instead. It would make it a lot easier to, we'd have easy access to the accelerometer, and it would also reduce the protrusion from the leg. And we would replace our running belt. We need a bigger one because our breadboard doesn't currently fit all the way into the pocket like we initially expected it would. And we'd like to try to contain all of that at the hip instead of in the front. I'm going to pass it off to Andrew to talk about our identification.
So one of the most crucial parts of our system is that it has to identify a person based on the wall. So essentially what this part of the system is it takes the raw data sensitive from the electrical systems and the sensors, which initially was acceleration and velocity. Then we filtered it with a low-pass filter with a cutoff frequency of 10 Hz. That's to eliminate noise from like vibrations against the skin and at the waist and stuff. And then we were going to integrate it and then calculate the joint angles based on the values that we collected. And then we were going to calculate the Fourier coefficients of those values and then put it into an artificial neural network. We decided to change a lot of things about this. First, we got rid of the integration and conversion of joint angles part because, one, it adds a lot of error, and two, it was a lot of math that we did not want to deal with. So we replaced it with something that I call segmenting, which essentially took away the first step of the system, which could vary within one person's data sets. So that helps increase the accuracy of the neural network. And it also improves the accuracy of the Fourier coefficient calculations. And we also decided to replace the neural network with a beg decision tree algorithm because we put it through the MATLAB classification learner app and it told us that the accuracy is higher. Additionally, the beg tree algorithm is a lot more transparent than the neural network, and you can actually identify how it's making decisions. So I'm going to do a quick run through of basically how we process the data so that we can make it acceptable to the neural network. So first, this is all of the data that we collected from the sensors. As you can see, some of it's relatively noisy, but especially in this particular one, the rotation about the z-axis, it's very periodic. So after we took the raw data, we filtered it, looks a little bit nicer, and then we decided to look at the one that had the most prominent peaks so that we could identify periods of the data very easily. And this is a bigger picture of that. Then, this is the segmentation process. We found the first peak and then the next 4 peaks afterwards of the data so that we could remove all the extraneous data, which then looks like the picture on the right. And then from those waveforms, we can calculate the Fourier coefficients. And as you can see, especially in this data set, the data fits very nicely to the ecliptic curve. And then these coefficients are what we actually put into the neural network for each of the variables. We used just the gyroscope data in the end because the acceleration data did not improve the accuracy of the algorithms. And then, in order to do all our testing, etc., we developed this little GUI, which allowed you to detect or choose how long the test is to actually collect the data, and then give you feedback on if the data was successfully collected or not. To select the test subject for saving purposes only. This is not affect the neural network at all. And then we have a button for guessing the subject, and then we have buttons for pistols hitting the Bluetooth mechanism. In order to test our identification algorithm, we had to train the data. When we first started collecting training data, we actually collected it with data that we did not end up using. So in that set, we collected 20 to 30 sets per subject, subjects being the 4 of us, and one set of other, which included up to 6 other people that would be considered a failure for the system. That set, we threw it all the way, and it took 60 more sets for every subject. And then, once we collected the data, we used that to train the algorithms. And then, in order to test the algorithm, we ran 10 more trials for every subject through the algorithm and saw who it identified, which we'll discuss a little bit later. Some improvements that we would like to implement to the algorithm. One way would be to implement an even better algorithm than the bag tree algorithm. It's called a random forest algorithm, which is basically the same thing as the bag tree algorithm, but it helps prevent overtraining. We would also like to take more data, including more intruders, which would be people that aren't officially recognized by the system, but allows for detecting more people with different types of gates. And we'd also like to implement a function that allows us to identify more people by name relatively simply. And then now I'll pass it off to Danny, and we'll talk about the results of our project.
Thank you, Andrew. So after telling you how we did all this and kind of all the trial and errors that we went through, we'll tell you about our results. So as you can see here, this is the 10 trials that we took after we retrained the network after taking all of those other 60 data samples. And you can see that it identifies Andrew 90% of the time, Eugene and myself 100% of the time, and other 100% of the time. There was an issue with Katie only being identified 50% of the time. We currently believe that may be because Katie is one of the more neutral walkers in the group, so her data more resembles either mine or the other group. We will probably look into that a little farther before the design expo, hopefully, but the total success rate of our system is 88%, and our SERG actually says that we should have a 75% success rate. So we're kind of taking this as a, yay, it works, 88%. The kind of total cost of our system, the per unit is $98.69. Overall, we spent $175.71 on all of the materials, the extra Bluetooth that we needed to purchase, and the extra materials that we needed just in case we blew anything out. Thankfully, we didn't, but we had all of that stuff just in case, and if we ever need to create another unit, we have all of that material. So again, some lessons learned was to always thoroughly research the components. I know it's a thing where you kind of find a component that you really like, you say, yes, it's perfect, and you buy it, but then it doesn't actually interact with other systems very well, or it's not as easy as you thought it was just because some forms that it'd be a great tool to use. Always an open mind. Something that we learned is there are multiple ways to do something, and don't get fixated on doing something one way because there are other ways to do it, and sometimes there are better ways to do it. Documentation is important as well as time consuming. It's important because it's how we know what we did, and so if we come back to it in the future, we can figure out how we did it again. And it's time consuming because that takes a lot of time to actually put what you're thinking down into paper into a way that other people understand, but it is super important. We always should buy extra batteries. Batteries are important because we do not have the low power mode. Things can be used up kind of quickly, so we always want to have extra batteries on hand. Also, always ask for help when you're struggling. I know it's kind of it's bad pride, but always ask for help because no one's ever going to fault you for saying I need some assistance. So we talked about today the project definition, the system overview, some of our subsystems, the results, our lessons learned, and now I have some time for questions. Does anyone have any questions? Yes.
So in your result that you only had 4 trained individual and others. How do you think your system would perform if you have, let's say, 20 people and then you have to classify out of the 20? So 4, maybe it's easier for the system because you only have 5 options, but now if you have more options, what do you think will happen to the system? Is the accuracy goes down?
So the question was, how would our system handle if it had to identify like maybe 20 individuals instead of just the 4 of us? Most likely, the accuracy would go down, especially if you have people with similar gate patterns. That's kind of evidenced by the fact that Katie was identified only 50% of the time instead of the higher rates. And so that is probably what would happen. But we'd have to do further testing to verify that.
I have a couple of questions. One is, you said you needed a minimum of 20 hertz sampling rate. Where did that come
So the question is, where did we get the information to determine that our minimum sampling rate should be 20 hertz per system? So what we did was we actually took the data from the Extend system, and we were able to look at plots using fast Fourier transforms on it, and we found that a lot of the harmonics on the greater end tended to be below 10 hertz. So it's around mostly 7.5, which led us to determine that the minimum sampling frequency we need to actually be 15 hertz. However, it's not the safest idea to stay at the minimum. So we decided to up the sampling rate to about 20 hertz for safety's sake.
Great. My other question is, I'm curious, do you know why the bag tree algorithm would be better, or maybe the random forest would be the best? You know, what characteristics of those algorithms make that?
The question was, why was the bag tree the best? Not 100% sure. I can theorize. It was mostly just we picked the one that had the highest accuracy from what MATLAB told us. Part of it, I think, is because decision trees are very good at classification. And neural networks can be very good at classification, but they're not always. And then decision trees are
All right, thank you guys very much.
Okay, about a 5-minute break, and be back at 11:30.
Yeah, she did. Oh, yeah, she texted me that she understood. So I think the picture is pretty good.
Either that or it wasn't the show.
I think I'm blaming Amanda because we used her as an other, and I think our water was the most similar to mine. And I think that's why. I think she's trying to walk with it. Messed up.
So you're streaming this on wireless.
That's what I'm thinking. So any other girl that we have to have all these other
So the one that's the live streaming will be up there and getting her first videos process. But I did record my first once those get uploaded, not just like what is
Put that in or down.
if you don't pick up a series about 30 years,
Yeah. So James did he just do
Yes, like I can make it.
I don't think there's a single better one than the morning section. There's ours is a great call. Yeah, last year they did a study of parity of life. Just like this. Are you? Oh, you're gonna jump?
That's not that right. Oh yeah. It's the same on YouTube videos. Right now, once I get through the including two sets. No, there are I think two. This one should be 3 more. Yeah, I think one for now. Type in like your group's name. Get one to make it public. Yes. Oh, the listed. We all did some cameras. Yeah, right. You guys can still see it. Yeah, we want to show off. Friendly. That's why.
Hello everyone, we are Fantastic Plastics. Today we are going to have a final design presentation. I'm Maisie, and here is my team members, Lucas, Hazil, and James and Lucas. And our advisor is Riva Johnson, and our customer is Daniel Blood. Here is the outline of our presentation. We are going to talk about the project definition, shredder and injector subsystem overview, shredder subsystem, test plan for the shredder, and the improvements for shredder, electrical system for injector system, mechanical subsystem for the injector, and the mechanical subsystem for the injector subsystem, pounder subsystem, test plan for the injector subsystem, improvements for injector, and in the end we will answer questions. Here is the project definition. We are going to design a shredder and injector to take the recycled water plastics and other plastics. We will be working with 4 kinds of plastics: PLA, PET, ABS, and nylon. The shredder will take the plastics and shred them to small enough pieces and to be melted them. For the injector, we will take 4 kinds of plastics and melt them. Here is the shredder subsystem. In this kind of model, we can see we have the 2.4/1 toggle ratio sprockets And we have the shear blade assembly, push blade assembly, and the housing for the shredder. And we have the top lever here, and its length is perfect. Here is the injector subsystem. We have the electrical housing and the thermocouple here. We have the band heaters. It's 6300 watts. And we also have the brass pipe. Here is the existing subjects for our injector subsystem. Let me pass to Hazil, and he will talk more about the shredder system.
Thank you. So now we're going to go talk into more of the mechanical components that went into the shredder subsystem. So as Macy just mentioned, I just wanted to point out there was one that was kind of hard, which is the incline. And that's just a piece of plexiglass that we put in there that you can have the plastic just slide down into where all the cutting action is occurring. So here you have the exploded view, and you can see everything that's inside our system. So you can see we have ball bearings in the inside, the sprockets are contained, and you can see the actual alignment that we had to go with. And then here's basically everything back and built together. So first off, we're going to talk about our housing that we made. It's made with aluminum 6061 alloy, so it's pretty easy to machine, and we actually had to machine. We use the CNC in the manufacturing lab to make our holes, and as you see, we have 3 holes, but this was due to an error in because our first iteration we were going to use gears, and so the 2 holes down here were made for gear meshing, but we ran into a mistake, which later James will talk about, but this third hole is what was our final design, so we have the rod going from here, and that is how we get our cutting action. Also to note is the corner brackets. These were corner brackets that we used to make sure it would stand up on its own, but later on we wanted it to be stronger, so that's something that will be something we can improve on. Moving on to the push blades, our hex rod that you see here was sponsored to us by Mizumi, along with a bunch of ball bearings and other parts that we requested from them. So the hex rod is made of steel. This was laid down to get it into a more circular shape so it could fit into the ball bearings. And then these aluminum blades, there's like 3 iterations of them, and each one is basically offset by a couple degrees. So this was used to push the plastic into the into the shear cutters, but just to note this design, we researched this design, so this was what we determined would be the best way of cutting our plastic down. So here's the cutter assembly, and this is what is actually going to be shredding against the push blade. So the push blade would just be basically rotating, and in between all these gaps, that is where the plastic is being shoved into and thus being shredded. And this was manufactured as well in the manufacturing lab. We used a plasma cutter to make sure that we got the right size, but unfortunately for the thinner ones, it was a really nice finish, but as you may have noticed that the thicker ones were just a lot thicker, the aluminum, it was harder to get a nice finish. So an improvement to this could have been going back and making sure all our edges were really sharp for a better cutting action. And then we have the lever. The lever was something that was just because we wanted to make our system fully mechanical. We could have attached a motor to it to increase our torque, but since we were doing it all mechanical, the lever would be the input to the drive shaft. And so we MIG welded this together for here as well at Valpo to make sure we had enough torque, and the amount of torque we needed to shred a barbell was, we measured it this time, and with all our torque amplification, we got it to be like around 8 foot-pounds. And now I'll give it to James to talk more about the rest.
Thank you. So from the beginning of our design, we wanted to implement a torque ratio to make it easy for the user to actually be able to shred the water bottle, because we don't want it to be a workout. So we came up with, our first design was to make it gears, but we found that purchasing steel to make gears thick enough that would withstand everything would be very hard to do, or not very hard to do, very expensive. And so we ended up coming up with this sprocket design. And so basically we get the 2.4 to 1 torque ratio by there's 24 teeth on the big gear, and then there's 10 on the small one. And then it uses a ANSI size 40 chain, and then you basically use a lever to crank it, and it basically works like a bike pedal. Going over our shredder test plan, these were our main tests that we did. And the first one we did was be able to shred the water, PLA, ABS, nylon, and the other different materials down to overall size of 0.5 cubic inches. We chose 0.5 cubic inches because that is what we determined to be able to fit into our into the injector for the later melting processes. After doing the test, we took, for the test, we took 25 samples of each material, or at least we tried to. And for the water bottles, we were unable to shred the water bottles and we just smashed them. It tore a little, and then I'll mention what we can do later for the improvement section to actually make it shred them. And then PLA, it did fairly well, but we found, like as we put, because we took different failed prints and put them in there, and the bigger the size, the more force it was putting on our back wall, and it actually ended up bending our brackets on the back wall, and then it made it very weak, and soon, by the end, the PLA pieces were just falling down through the cracks in the spacer because the wall kind of separated from the back. And nylon is a very strong material. We attempted to do that, and it just required too much force, even with our torque ratio. And we thought we would just totally break our back wall off, so we just failed that one. And so for the PLA, it was an average of 1.5 cubic inches in size. The sizes just got bigger as they went along because of that separation in the end. And then our second test was the force applied by the user may not exceed 180 newtons. We used a torque wrench and welded a little nut on to be able to test this. We found that for water bottles, it only required 8 pound-feet for it. And then for 3D prints, it required about 88 newtons, which is about 20 pound-feet of torque. And then for the emergency shut-off mechanism, our original plan was to use a bike brake to stop the gears. But since we implemented the sprockets, we were unable to use that bike brake because there just wasn't enough clearance room. And so we ended up not having a safety mechanism just due to time constraints and our design change, which we kind of just forgot about the safety mechanism overall. But we aren't too concerned about it because we don't expect someone to shove their hand in there. Well, I hope they don't at least. But so that's why we failed that test. As far as shredder improvements go, like I said before, we need stronger supports for the walls in order to actually be able to handle the force required for shredding. And so when we were at Menards, we bought the cheapest brackets possible to save money because we didn't know. They actually have thicker brackets out there, and we could implement more as well. So that could help a lot. And then for the push blades and the cutting blades, we could sharpen those, and if we sharpen those, that would actually reduce the force onto the wall as well, because it would require less force to actually shear the water bottles and other materials that we're putting through there as well. And then we could come up with a safety mechanism that would be a major improvement. And then we can also mount the bucket. We found that when we have the shredder on top of the bucket and you are using more force, it tends to wobble. So you have to tend to have another person actually hold it to make sure it doesn't fall over, and that you can actually get the force required to actually make it shred the materials. And then we did design the shredder to be able to handle motors with a keyed shaft, and so we could just remove the handle, and if the customer did want to implement a motor in the future, it's very easy to do. What we learned? We learned to check SolidWorks many times before actually joining the manufacturing lab because, as Javier mentioned earlier, when we did CNC those holes, we did them too close, where we were only concerned about how the gears were meshing, and we didn't actually consider where the push blades would actually be, and we found that the push blades would just ram into the shear blades, which would not allow rotation at all. We also could order parts earlier so that we could actually, which would result in us being able to build it sooner and then test earlier. Because if we tested earlier, we could definitely make some major improvements and actually had a subsystem that works. And then prepare for manufacturing failures. We had many plasma cup failures just because the tolerancing was off. Many times when we were trying to tolerance the hex on the actual push blades itself, it would be too big because the plasma cutters doesn't hold too tight of a tolerance. So it's really about designing for manufacturability. Because just because it looks perfect on CAD does not mean you're going to produce in the real world with given tools. And then we also learned that stock metal is very expensive, especially when you screw up. I had to order many more pieces than it was not fun. Now I'll pass it to Thomas to talk about the injector subsystem.
Sorry, the back fell off earlier. So here's our injector subsystem. A little background of our injector subsystem is that one of our design requirements was that we had to run on a 48-volt battery, which is based off solar, because our project was going to be used in Haiti. And in Haiti, they rely a lot on solar power for reliable power sources and things like that, because after talking with the customer, I realized that they're actually, I think they, I don't know if they're 120, not AC, is not very reliable down there, so running off of a 48-volt battery, or their solar batteries are very more reliable than running off their AC. So here's an overview of the electrical subsystem of our injector. So we have 5 main parts of our electrical subsystem, and all these 5 parts, if you look, fit into this nice little electrical box right here. So our 5 parts are the MT430 microcontroller. We have the thermocouple amplifier. We have the buck converter. We have the solid state relay. And then we have switches and external resistance. So to talk about it, we have to talk about voltage breakdown. Because as I mentioned, our requirements are around 48 volts, so I will start talking about 48 volts. So on the 48 volt side, from the shoulder battery, it's not a consistent 48 volt. You can range anywhere from 45 to probably 55 is probably a solid range for most of the batteries will run. So one of the most important things about running the system is getting a good buck converter. This is our buck converter right here. So in calibrating our buck converter, we calibrated it to be take the voltage range from 45 to 55 volts or some range like that. Even lower, it can go I think to 12 volts or something like that. And output 5 volts consistent. And through testing of just using a 48-volt battery, we saw different voltages. I think we saw personally went up from 52 down to about 49, 48 volts, running on an actual 48 volt or out of the 48 volt battery. But consistent 5 volts were output from the system. So running off a 5 volt system were our MST430, our microcontroller, and our thermocouple amplifier. So the microcontroller was like the main component of most of our system. The microcontroller controlled everything. The heating of the system controlled when heat was applied to the system, or when voltage was applied so the system could heat, when voltage shut off, and was controlling the switches so users could select things like that. The thermocouple amplifier, which is shown here, was needed because thermocouples, when they measure heat, they measure the voltage difference between two types of metal. And they output voltage difference. Well, the microcontroller could not read that small voltage change. So we got the thermocouple amplifier to amplify the voltage. So the MST430 successfully read changes in voltage which equate to change in temperature, and then change based off the different temperature changes. And then we have the solid state relay. The solid state relay is what actually switches power on and off to the heaters or external system. So whenever the solid state relay would get voltage to the microcontroller, the solid state relay would then turn off the heat to the turn off power to the heater so the heater cool down. And then when it goes below a certain threshold set by the thermocouple amplifier, they would then turn power back onto the heating resistor to power the system back up. So then for user identification, we have 4 external switches corresponding to 4 plastic, PET, nylon, ABS, and PLA. So whenever a user wanted to select a certain type of plastic, gives these different types of plastic, had different melting temperatures, which each were set to a certain melting temperature. They would they would pick the external switch they wanted, and then it would go until that temperature was reached. It also had 2 notification functions. It had a green LED, which when the switch was flipped, which means the system was turned on, the green LED would turn on, and then a red LED, which correlated to the system was ready to inject. So once the temperature was reached, it would go into an oscillation period where the voltage would be turned on and off based off a certain range set in a microcontroller. And once that light was on, it notified the user that, hey, the plastic is ready to inject. So now I'm going to hand it off to Lucas to talk about the mechanical system.
All right, so our injector's mechanical system has 4 main components. We have the heaters, the thermocouple, the plunger, and the frame. So our heaters are 120 volt AC heaters, come off Ranger. They're 300 watt heaters, but we only run them off 48 volts, so they actually only output 48 watts. So our total heating system is only 288 watts, which is a lot lower than we had originally assumed we wanted to do at the beginning of the year. So our thermocouple is a J-type thermocouple. We got the wire from Professor Venstrom, and he also helped us weld it to get a good junction. And then we're actually, if you see this picture, that metal band was actually supposed to go around the heaters, but the pipe was so much bigger we didn't need it. So we're using that metal band to hold on the thermocouple because you cannot weld any sort of, like, it's just iron and then, I can't remember the other one, and you cannot weld that to brass. So we actually need to crimp the side. If you see all the way on the right side of this metal, it is kind of like twisted a little bit. That's to get like a good pressure on there to basically create a mechanical junction. Our frame, we actually got 1-inch square steel tube stock. We got a lot of this, and we MIG welded it together. In-house manufactured. It's around 3 feet tall, and then each of the side like chunks coming off are all basically about 1 foot. Worked out pretty well, and it was very sturdy. We had blood in one of our tests putting a whole lot of force down on this, and it was completely fine. Our plunger, we made the plastic out and into the mold with enough force to mold it well. We used 1-inch square steel tube stock, 1-inch round steel tube stock, and 1 1/4 inch brass stock. It looks kind of weird to use a bunch of different stocks. That was just to save money. So the square stock at the top, making that T, was MIG welded together, and that was actually just excess material that we bought. That's the same thing that we used for the frame. And then we also MIG welded on the little mid chunk of the circle there. That's your round steel tube stock. That was extra from the handle for the shredder's lever. And then we got 1.25-inch brass stock for the bottom. So we actually had to thread the steel stock and the brass to get a good connection there. Brass basically serves the purpose of being the same inside or outside diameter as the inside diameter of the pipe. And then because of the same material, they don't expand weird, and we're not actually making pressure fit by accident. I'm going to let Thomas talk about the injector test plan.
So for injector test plan, some of our major test plans are broken down into these 3 categories. The first category is to maintain melting temperature, or melting chamber temperature to be within 265 to 280 degrees Celsius in under 10 minutes. That 265 to 280 is about the highest range that the types of plastic would become resistant. So that's why we got that type. And the 10 minutes was just a SDRD specification. Unfortunately, we failed this. We were not able to reach that temperature at the time. We were not able to reach that temperature in an extended period of time. So that one was failed. Our next one is notification of the user. and we passed this. So the injector was able to notify the user when the injector was on. It was able to notify the user when it reached a certain temperature, and it was able to notify the user by the switches which type of plastic that the user had selected. And our last safety features, we passed out safety features that we wanted. Our kill switch was able to cut off power to the system when the user flipped it, and did multiple tests worked every time. There was no power when they turn off the safety switch. And the outside temperature of installation when around the pipe during heating always remained 70 degrees Celsius.
Right, and then some improvements we can make to the injector. We could have implemented a 48 DC to 120 volt AC inverter. This would allow all our heaters to run off of 120 volts, which would have given us 300 watts out of every single heater instead of 48. So instead of running at 288, we'd be running at way more than enough watts. We'd probably have issues with the brass pipe at that many watts. Then we can also upgrade our installation. We just kind of use basic pipe installation like what you have in your house on the water pipe. We can upgrade that, make it a little bit thicker, go for something that isn't just the fiberglass insulation. And we can get more wattage. So, like I said, there are other ways to do it as well, but we can do it off the inverter as our best, like our second, our best choice from there. That would allow us to get to the temperature that we need in probably a short amount of time. So some things we learned while we're working on the injector. We learned that SolidWorks thermal simulation really does not do anything to simulate perfect. So it doesn't have any heat loss or anything like that. So we really had to accommodate a little bit more for losses that are just real world issues like airflow and the whole thing not being completely covered. We're also running 48 volt heaters, or running the heaters at 48 volts really does not provide the amount of wattage that we need to get the pipe to heat up to where we want it to be. So we can definitely improve on that. We also know that scheduling is very difficult, so we always had to test the injector while blood was in the room because we operate off the forklift battery. And that really causes issues because generally he only has like 1 hour of free time every Wednesday and Friday that we could release. So testing very often was quite challenging. We also learned that testing really would be very nice. We started testing significantly earlier than we did, then time constraint of blood would not have had such a huge impact on our injector. And then, same as before, buying stock metal is very expensive. So if the injector brass was a big killer, that one was extremely expensive. It was like $58 for a foot and a half of the brass piping. In summary, we talked about the project definition, the shredder and injector subsystem overview, the shredder subsystem, the test plan for the shredder subsystem, improvements for the shredder, the electrical system in the injector, the mechanical system in the injector, the plunger subsystem, the test plan for injector subsystem, and the improvements for the injector. Any questions?
On the electrical side, you had talked about that a little bit. You said there's a solar cell, there's some 48 volt part, there's a 5 volt part. Can you detail, so the solar charges the batteries, so you've got batteries that are not 48, they're in between 52 and 48 when they're charged. And then you step that down to 5 volts?
Yeah, so the question was just to explain I guess, how the 48 volts works. Yeah, do this and then pull it up. Yeah, sure. So again, for the 48 volt battery, they eventually step down to some, I'm simplifying the process, the actual process, how the solar gets into that, how it gets 48. But it gets 48, or 52 to 48. Well, then what happens is, we run that voltage into our box, and we attach it to our solid state, which is like the main power source because it handles, it can handle 48 to, I think, end up 60 volts. And then from that, we attach a buck converter, which will step that down to 5 volts. So the microcontroller amplifier can run. One of the nice things if we did run the inverter is we would be able to do most of this in mainly 2 components. We do a solid state relay that handles AC and a PID temperature controller where the user could set the temperature to basically everything. Unfortunately, due to constraints of money, other things like that, this was the route that we had.
You're not regulating that 48 because the buck converter is next to it. Okay, so you're just using the SSR to switch whatever's coming out of the battery that goes directly in your resistor heating coils?
Yes.
Okay, then how much current do you need for those coils?
So each of the heating resistors, the question about how much current you need each of those coils. Each heating resistor is 48, because it says heating resistor. Each of one is 48 ohms. So if you assume 48 volts going in, it's about an amp of current coming out per heating resistor. So they're connected parallel. So in total, I think we're running under 7 amps of current for our system.
7 amps at 48 volts.
Yeah.
Any other questions?
Professor?
Do you know how long the battery lasts with your system now? It dies completely?
So the question was how long the battery lasts operating our system. We do not. We didn't have issues with our battery on the 4th year. The ones that the professor was planning on using in are, I think he said around triple size. So it could be operated for a pretty long time. Some of our operations actually ran for around 40 to 45 minutes, and it was only supposed to be running for like 10. So it's not having too many issues with current draw.
Any other questions? All right, thank you very much.
Everybody is changing his cards as well. He's on PowerPoint tools, we're just trying to figure this out.
Otherwise,
Good afternoon, everyone.
My name is James Larson. These are my teammates Christian Lehman, William Parsons, Joe D. Our advisor is Professor Roscoe, and we are presenting on behalf of the Contact Solutions team with our concussion monitoring and detection system. So today, we will discuss the problem definition, go into the system overview, look at our testing and results, talk about some lessons that we've learned over the last year. We'll recap everything with a summary, and then we'll have time for questions. So first, let's talk about our problem definition. So at the beginning of the year, we were assigned to create a concussion monitoring and detection system, which is a wearable device that measures and stores impact data so that it can later be analyzed to determine whether or not concussive impacts have occurred. So once we were given this problem definition, we immediately Googled how do you know concussion? And what we learned is that nobody really knows. I often tell the story that I sat in an hour-long presentation with Harvard PhD students just for them to say the area in, and we just don't know. We spent an entire 4 years trying to figure out concussions, and we don't know. So when we started the research, we had to really cast a wide net to figure out any and all variables that we could attribute to maybe determining the risk of concussion in our athletes. We found a lot of really interesting stuff, but the most relevant research that we found came from a man named Stephen Rouse in his paper titled Rotational Head Kinetics and Football Impact and Injury Risk Function for Concussion. So, for those of you who are great at interpreting paper titles, he let us learn about rotational head kinematics and football effects, and it gave us the function to predict concussion. So these two tables were one of the two big things that we pulled from this paper. It gave us, on the bottom, these were sensors that he had placed in football helmets, like American football, to determine whether or not concussion impacts had occurred. We're using an accelerometer and a gyroscope to measure linear acceleration and angular velocity. And when a concussion had occurred, they would record the values that corresponded with that concussion and give us a standard deviation. From this table, they derived this table up here, which told us for a given angular acceleration or angular velocity, what we could expect the risk for a concussion to be. Now, the issue with this study is that these were helmeted football players, and we are dealing with unhelmeted soccer players, and so there was a risk that we were taking to use this data because, for all we know, this data could be largely skewed because of their helmeted head kinematics. So does the helmet change how the head moves? Would we, the soccer player would receive something 10% of these values, would they get a concussion? So there was a lot of unknown in us deciding to choose these values, but what we ended up discovering was that actually through a mouth guard, football helmet, or a headband, most of them actually have the same, relatively the same ability to measure kinematics. So we went ahead and we took these values and we decided that this is what we would base our project on. What we finally decided with our solution was to, like Rouse's paper, we decided to use a gyroscope and an accelerometer because those are the two sensors that would allow us to measure the two most correlated variables, that being linear acceleration and angular velocity, to determine whether or not concussive impact occurred. So you can see here, this is our model headband, and this is where we store all our sensors in the back of the head. And so what happened is a soccer player would wear this headband, and then once a predetermined threshold for angular velocity or linear acceleration had been surpassed, there's an LED on the back of the head that would light up and signal to our players, hey, you can pull to the sideline and evaluated by a professional. Now we didn't use these values on this page from Rouse's paper because this is a guaranteed concussion. You're like unconscious on the field. It's plainly obvious that you're in a terrible state of being. So we chose values that were significantly lower, so maybe this 25 to 50% range, because we want to know before you have received terrible brain trauma, we want you to be able to get pulled off the field and evaluated by a professional before it's apparent to everybody else that this is a concussion. Additionally, we stored this data on an SD card, as you saw in our problem definition, because we had to analyze this data later. There's a lot of talk about subconcussive impacts, so impacts, like we said in the last paper, that don't immediately knock you out, but if you receive a bunch of subconcussive impacts, does that later make you more susceptible to
concussion. So we wanted to be able to use this as a tool not only to alert the players whether or not they were in imminent danger, but also to be able to gather this data for the effective research later on down the road. So getting into our mechanical sub-assemblies here, the big thing that we worked on was sensor housing. So this is this blue piece here, and we included a cutout over here, and this is exactly how our sensors are stacked up. And we made this out of a 3D printed nylon. We found that this was a cheap, durable material that would really safely allow our sensors to be put into the housing. It could receive impacts. It passed all our FEA analyses, and it really performed well as a material. It was easy to slide this white slide right here. It's slid out to allow for very easy access to the sensors should one become damaged and need to be replaced. And we were able to attach these to our headband via hook and loop patches, which are just off-brand Valpo strips. And actually, we were able to, it's modular enough to where we were able to attach this to any number of headwear, such as hats, helmets, you name it. We're actually, it's pretty modular. This is going to be fun. We have a video of that attached. One of the other sub-assemblies we have is the Halo headband. We've talked about this throughout the semester. This is just an outstanding headband. We've had it on our styrofoam head for months and it hasn't deformed. It really does it well for the sweat. Very comfortable to wear. We ran studies and we found that at 50th percentile metal head, it fits entirely on the range, thanks to also to Danny. We found that it fits a very small range head, so we're covering all of our bases. She graciously agreed to help us test that. And you know, with moisture, it does everything you would want to. It would want to do as a soccer player. It didn't interfere with movement. By and large, you find it a non-intrusive addition to your athletic gear you really know you should be wearing. So this right here is the structural cloth we decided to use to attach our headband to our units. And play this really quickly just to show. So ideally, we'd be able to use that to show you how we would attach that to our headband, but it's just as simple. There's two strips on the bottom of the 3D printed housing. It attaches to the headband, and you roll it around the condition it's attached to, and then you just bring two other Velcro strips around and secure it. And it's not inclusive in the testing that we've done. We find that it's very comfortable to wear, and allows for very modular attachment to different types of gear. So with that, I'll pass it on to Joe.
Thank you, Jake. So as you can see here, this is our electrical sub-assembly. For our sensors, we had accelerometer and gyroscope. This here is the accelerometer and the gyroscope. So the accelerometer we used was an 80XL 472, and the reason we decided to use this is because it had a range of plus or minus 200 Gs, which covers the full range of what could possibly be concussion. And it also went up to a sampling rate of 3200 Hertz, which met our requirement of a minimum of 1 kHz. So going on to the gyroscope, we chose this one because it has a range of plus or minus 2000 Hertz per second. And as we saw on this slide here, the 90th percentile for rotational velocity per second is 33.2 radians per second. And converted to degrees per second, it is just over 1900. So our range of plus or minus 2000 degrees will fully cover at least the 90th percentile. And we determined that if you reach the 90th percentile, it's very likely that you're going to have a concussion. So reaching that full 100% was a necessary requirement. So, going back to the electric sub-assembly, we originally had the MSP 430 FR5994, and once we got to programming this, we found that it was very difficult and it was out of our scope. We just didn't fully understand everything that was going on, so we decided to opt for an easier thing with the Arduino Mini 5. And since it was so easy, we also incorporated the SD card shield, Arduino SD card shield, so that we could easily read our data. And this was very nice because it made for a seamless, easy transition into recording data. So moving on to printed circuit boards, they're very cost effective and size efficient. We use Corel Draw here in the labs to create this with laser etcher. Each of these PCBs is size 2.2 by 1.6 inches. So here you can see this is our power supply board. This here is our Arduino board. This is the board that we use for the accelerometer, the Excel. Sorry, this is actually the BMG board. This is the Arduino board. And then this is the SD shield. So with all of these, we had to connect them with soldering, and that was a big challenge for us because we ran into a lot of issues, voltage problems. So originally, we had the Arduino going on 5 volts. And we determined that since the Arduino, thanks to Professor Will and his expertise, we determined that the Arduino has its own internal voltage regulator, so we didn't give it lower voltage. So we decided to connect that to straight 8 volts, and then each of these things here is a voltage divider from those 8 volts to give the SD 5 volts, the ADHL 2.5 volts that it needs, and the BMG 3 volts that it needs to operate. Where we ran into this, we ran into connection issues possibly between here and here, which actually ended up frying our sensors, which is a very big problem that we ran into. And yeah, so we found that soldering is a very large issue. And now I'm going to pass it on to Christian to talk about the system review.
Thank you. So here I just have a diagram to give you a basic idea of how the systems work as a whole, all these separate parts that we've been talking about interacting. For the most part, it did what we wanted to. Like Joe said, the problem was actually integrating the systems into the final product, and we started using PCBs. So we'll start here. We've got our sensor array up here. We've got the accelerometer we're talking about, the gyroscope here. Both of those serve about the same function. They receive requests for data from the controller shown here, and respond back with their respective values. The controller handles all the conversion rating and all that kind of stuff, and then handles the units. What happens down at this part of the system here is when the controller detects a rate above either the 40G linear acceleration that we chose, or I believe it's about a 1740 degrees per second rating from the gyroscope. At that point, it saves all the data that it's been collecting for that impact into the SD card, refreshes some data registry stuff that we'll get more into on coding. And at that same time, we'll light this red LED here that tells you, hey, a concussion or subconcussive level impact has been detected, this player needs to be pulled. And then we had an extra green LED to just show that all the setup inside the code was complete. Most of that was so that you know to wait for the system to finish booting up before actually trying to take the measurements. So here I'm going to go over the actual algorithm that was going on inside the microcontroller, the programming side of things. We have this whole, we have a whole block up here that all the setup is happening, so we configure both the sensors, initialize the SD card, and then also set up timer interrupts that I will talk about later. From there, we had a 30 data point register that would store sort of like a FIFO. If anyone's familiar, it would store 30 points of data on either side of an impact, so we can make sure to capture the full impact spectrum. It would shift that data, read a new value from both sensors. From here, we would look at the, I'm sorry, it was 1432 degrees per second. Would read the impact levels, check, is this above the value that would lead to a concussive impact? If yes, store the full impact, clear the register and reprocess again. If not, it would just shift the data over and keep repeating. To make sure this is all synchronized, that's where the clock came in. As you can see, I've listed here, everything happened at a rate of 400 hertz. You may have noticed that's significantly lower than the 1000 hertz that we originally had for our design.
We ran into some complications with the Arduino. In order to run something on I2C at even 800 hertz, you need a minimum clock for that going at about 400 kilohertz. That was the absolute maximum that the Arduino Mini could even run, so we had to go even lower than 800. The next enable being 400. So we had to significantly cut back on the rate we were sampling data, but we still believe we could sample an adequate sample from that rate. Here's just a few of the resources that we use in the programming of our device. So I2C communication is a big part of this, and is actually where a lot of our notation came from. For those who aren't familiar with I2C, all of the binary communication happens over a single wire. So when the controller sends a signal to the device it's controlling, that all has to finish before any data can go back. So all the requests for data to the sensor had to be complete before we could get any data back. This is what really slowed our system down. Future iterations we might look at instead using SPI communication, where the to and from communication can happen simultaneously. Additionally, we built our own data register. As I said, that was the FIFO, or first out array. This was the block of data to capture the entire impact. It would shift data over each time we were adding a new sample in, so that we could make sure once the center point of that impact reached our threshold, it would capture the full spectrum. And then in addition, I want to give credit to the Timer1 library that referenced in the document. That was where we were able to synchronize most of our clock and everything like that, and simplify using the clocks built into the Arduino with custom commands, and let me use timer interrupts, which are not generally Arduino default system. So that's everything we have for the programming. I'm going to pass it over to Will. Talk about results.
All right. So for our testing results, as you heard from Joe, our sensors did in fact break.
So we did not get to test our final system, but this is some preliminary testing results that we got up here. This is with the gyroscope. As we see here, this is the 90-degree test, and it has it's got angular velocities that go up to 500 and down to negative 500, and then you have a smaller value starting position at 45 degrees, and you go 250 to minus 250. So it shows that our values are reading correctly, so we're getting the right data. And then that's just another starting point. It shows different max in there, which is great. But we never got to test the gyroscope and accelerometer in tandem, which really stinks, but we do believe that it would have worked based on this preliminary data. And the test that we were going to undergo would have been a late test to test the full range of the gyroscope and accelerometer, and then we were going to have an impact test as well. So we didn't get to do that. And then these are the design requirements that we met. The device did fit all head sizes that we wanted to, as we said, and it even went above and below. We went to 59 centimeters and down to 52 centimeters. And then the device did store data. That data that we saw earlier was retrieved from the SD card on the last slide. And then the housing was non-abrasive. That was based on material properties we pulled up nylon. And then our device only weighed 0.422 pounds, so much below our requirement for it to weigh less than 2 pounds. And then the sensors we integrated such that they could be replaced. We can replace our sensors. It would require some technical knowledge, but that wasn't in our SDRD that it had to be, didn't have to have technical knowledge to be able to replace it, so it would require a little bit of soldering. And then these are our unsatisfied requirements, and these aren't necessarily, the user wouldn't necessarily experience unsafe levels of heat, electricity, or blunt force, but we couldn't test these. Because our system broke, we could test the battery and see what type of heat it was putting off and electricity, but we didn't think they would experience that. And then the device did not have a sampling rate of 1 kilohertz, as Christian already talked about. It was 400 hertz.
The device will be able to remain powered. Yet again, we didn't get to test that with our full system. We could have tested it without the gyroscope. The gyroscope was the main current power draw. It pulled like 850 milliamp hours versus other sensor was pulling something like 100 milliamp hours. So we didn't want to test it and give our user inaccurate measurement on that. And then these requirements just fall off and not being able to be tested. We couldn't do any of these things because we couldn't test this. So our lessons learned, pick the microcontroller and then the sensors. Like we said at first, we had the MS-430, and that was really difficult to integrate with our sensors. But once we moved over to Arduino, everything got a lot simpler there. So it's important to pick things that you know can interface well before you even start. And then be prepared with multiple sets of backup components. And we were to some extent, we did have some backups, but just in the process of integrating everything on the PCB, some things did get broken already, so we didn't have enough backups. And then ensure documentation for hardware is accessible. So this really is what set us back in our project, time-wise. Our BMG250, our gyroscope, did not actually have a data sheet for the eval board, which means that we were just kind of guessing on pins that were on the board. So that we really had to wait for that. And that was a lot. That was like 4 weeks of communication with DigiKey and with the company that we bought the board from. And then specializing and working in parallel was very important in order for us to get our project completed. And sometimes deliverables have to be sacrificed for the good of the project. That's on the screen. But us sacrificing the 1K hertz sampling rate was what that was. Yep. So in summary, we talked about our problem definition, our system overview, testing results, and our lessons learned. And then, are there any questions?
So can you go back to the slide with the PCB?
Yep.
Okay. So so you were using the voltage divider, right, to get the to step down voltage. What ended up happening at the end then? I know we bypassed one for a voltage regulator.
So the question is, what exactly happened with the voltage at the end? I'm not sure how to word your question.
Okay, I know you were having trouble.
Right, yeah.
And then we got it half of the way. Where'd you get up at the end as far as the functionality?
Okay, so the question is, what happened?
Where'd you
so what happened was we found out that we needed to switch the 8 volts to the Arduino, which we did, and that worked everything fine. And then we had to change the voltage divider to 5 volts for the SD card, which worked fine as well. And then in the process somewhere, we're not sure exactly what happened or when it happened, the accelerometer actually broke, and we were getting a current voltage of 0 whenever we measured it, and so we knew that our sensor was grounded. So we restarted everything, put our backup component and everything in there, and then somewhere in that time span, both of the sensors that we had got broken. So then we had nothing.
So twice you used a passive verb, broke. So it broke. What happened? It didn't break itself, so was it a grounding issue, or?
It was, what I believe happened is we ended up getting too much voltage to the sensor, and then it overloaded it.
Nice active verb. Then the money question then is, you wind the clock back 2 months, what would you do differently?
What would we do differently? Use voltage regulators instead of voltage dividers. That would give us a better way of making sure we're getting the right voltages where we need them.
So I know that for your component housing, you did use a nylon 3D printing component instead of I think the default, I guess, is PLA. You said you got some constraint additions, I guess, to that component. So can you talk a little more about why you use nylon as opposed to PLA? Did you make testing with that?
Sure. So the question was, why did we pick nylon over PLA? And so we had done a lot of testing with the PLA that you can find in the manufacturing lab. And quite simply, if you drop it on the ground even, just the surface bonding between layers is enough for that pressure. And so In the worst case scenario where you receive a direct impact to the back of the head of a soccer ball, we knew that instantly everything would shatter and fly apart. And so in using nylon, you get a lot more surface adhesion layer to layer, which was huge for the strength of our product. But additionally, the density is a lot. It's a little bit lighter. It's a lot stronger. It doesn't deform with impacts. It doesn't really have as many critical points where it could fail and then start to slowly break down. A lot of even some of it too was that using the printers in Professional Lab, they have such a higher tolerance, and so that's part of it as well. So it was the nylon, but in addition to the tolerance of those printers allowed it to where with like the manufacturing lab, each layer is so far off that it's like they're building it out of critical points that are just all designed to fail instantly. So it was those two things together, accuracy and strength.
So wouldn't the PLA kind of act as a crumple zone as opposed to, so if you're being hit in the back of the head with a soccer ball, wouldn't you want it to crunch as opposed to stay solid?
So the question is, why did we design our housing to crumple when hit by a soccer ball, which is a fair question. Simply because it costs about $150 for the sensors and all of that. So it's a fair question. It's a fair question. It doesn't disperse the force. You still see that impact. It's not like it's going to just reduce the their head is still going to see that impact, and then they're just going to get burned.
Right, but now there's a hard nylon.
Right. Well, the housing is full of rigid, sharp silicon, so we could avoid that embedding into someone's head. That's a big part. So I feel like the blunt could be a lot easier to work around than shrapnel. It was basically our thought process.
Any other questions? Thank you.
I went over one star for Jim. I'm sorry. It's all good. So I went over it. Hello. I saw laundry.
Just like coming in like
No, we went over. Oh well. Technically. Yeah. I was freestyling. I was trying to.
Yeah, he went ham on those slides.
I was trying. Thank you for picking up. Yeah.
We told him that you were here changing and you're like just getting food.
So I saw this guy like my tidbit, which I ended up.
We just have to see you in Secret Design Expo where we get to tell people this. I called my mom. My mom was like right after the video tape, and then she like texted me. She's like, "So how's everything going?" And I was like, "Horrible." She's like, "Oh God, what happened?" And I called her, and she's like, "Oh well, you know." She's like, "But yeah, the whole time they'd ask me, so how's your project going?" Yeah, it's going well because it was going well. And then at the end, we were just freaking Donkey Kong pushed straight to the chest.
Yeah, there was that. That's a really elegant way of putting that. Ye old Danky Kang. Ouch. Yeah. What was the project? I knew I'd gone over to. I read Okay, this is how I see it, guys, and you can disagree with me. It was perfectly fine for you to not be here because you're an excuse, justifiable excuse. That required that all of you were prepared for you not being here. That's the only part. But if that wasn't addressed, then you had to take it of that, so like in a crunch time. Usually, yes.
Was it okay like the way we did it? Like
probably should have just I don't think it's gonna affect anything there. The thing is, at that point,
is less distracting. Right? You are lucky in the sense that the car is right there and you can just sneak in. Most situation you have to go through the back, so it gets distracted and it can distract you and things like that. So at that point, as I said, you were excused. It was okay for you to show up because you had that lab. It was just that you needed to coordinate before.
We were going on the assumption that I don't know how to figure it out. That was not before. No, I assumed that too much. I should have prepared. If you guys had few groups, maybe I couldn't tell you. But that was the assumption that was going on. But that was
yeah, when you're on the third, you always plan for more fees intercity, plan for those. And the worst is, okay, if he doesn't show up, he's arranging, if you show up, this is happening. And then you don't feel stressed out. But otherwise, with a little bit over the time, I think maximum size. You disclose everything, I think it was pretty honest in that I have not seen your videos, so I'm curious to see that. That's already available in the deliverables, the final design document. Did you guys work on that one?
Yeah, we turned it in this morning.
Okay. You guys should relax now. It is what it is. So now just try to portray it in the sense that of the importance that it has, because as I said, it does have importance. It is a topic that is still, people spend 4 years researching, there's no conclusive evidence. I'll post my comments that you see presentation. Relax a little now, guys. Our colleagues can run into these issues. I like that you remain a consistent team. When this happens, it's often for a team to fracture. And then that's very nasty. When I have to intercede and no one is happy when I intercede. I'm not going to be like when my two sons get into a fight, both of them get punched. So in that, I don't want to do that, you know. In this case, this is your project. You don't take it all. It's unfortunately what happened, but it's also good you take it. Yeah. So, okay, I will see you Saturday at 9 a.m.
Okay, so what time do we have to be here beforehand?
So now the expo starts at 10. So we're asking every team to be here at 9. So we can set up the booth, set up your poster, any power strips, and you know.
We weren't sure. I think we were under the impression it started at 9 and we had to be there before 9.
No, 10. 10. Yeah, 10 opens. We're already thinking ahead of here whoever comes late. Because we don't want to be setting up when parents and other faculty starts walking. So here at 9, we set up.
5 minutes here, flip ahead, and then watch another 5 minutes.
And once it's ready, only 2 of you have to be in the semester. I think we discussed that in the past. Only 2 at any given time. So you decide, you emailed me yesterday, you have to leave. You have to leave in the second part. That's fine, be here for the first part. If you cannot make it because of track, that's fine too.
I mean, practice.
Okay, I leave it up to you. The only requirements you discuss, you arrange how you want to do it, but if I don't see 2 of you at any given time, that's where things will go. Just because you need someone to manage the booth. Plan ahead. If you have that video, have a laptop ready there. Display, you have that dummy. Display how everything is supposed to work.
It is nice to have some.
That's what so he just markings on it.
So I'm having to compare this one and you're watching and someone
audio visual.
It's fun.
Is there any bloopers at the end that I should
well, there's not bloopers, but
everything is bloopers.
Our demonstration of our product is present.
Okay. I'll send you a video that it was done from 2006 CU design. Someone made a segue.
Really?
I'll send you that because it's not just that the segue is pretty amazing. It's amazingly done. It's also the video. So you can take a look. Alright guys, thanks. Relax. Just enjoy the rest, right? Thank you for that's a good semester.
With another project.
Ours doesn't work.
I'm going to be subtly trying to pass.
Alright, so how do we want to do? Okay, so we should do 2 shifts. It's 10 to 11, right? 10 to 10:30 and 11:30 to 1.
Yep. So I can do 10.
I'm down to do
Saturday practice time.
So yeah, I think I've definitely learned some stuff.
So we'll have to do probably 9 to
So really
9 to 11,
like
11,
Q&A, which
because
is
you
great,
setting up.
because then you do notice it.
Oh yeah,
live.
9 to 11. Yeah, 9 to 11, 11 1. Do you want to do 9 to 11 with me?
Yeah, well, I can't. I thought you had to leave.
I have to leave.
Q&A because otherwise, if there are 3 people.
Okay, so you can just be there with us.
Yep.
Okay, yeah, okay.
But yeah, this is.
Are you fine with that?
Very pleased with the way these
I'll
are
just show
shot.
whenever I'm done with practice.
Okay, yeah. One
One
of us will just wait.
We can
Okay, well, yeah. We'll make sure that.
Yeah, we'll figure it out.
I'll know what Saturday practice time it is today.
Joseph?
Yes.
I wasn't trying to be hard on you.
Oh, I know.
It's like the you're taught to say like I forgot some presidential speech and there was like mistakes were made. Now they teach you to do it. Like, mistakes were made. Something happened.